Yep. Okay, so now we can use, so we have, well, if we assume we know UI, then this one has two unknowns, and we have two different equations which we can use to find them. So we see that, oops, I can do, so when this R is 0, we should get 0 out. Okay, that means that U 0 is big U I big R squared plus C1 logarithm of big R plus C2, and that U speed of the drill string alpha squared R squared C1 logarithm of alpha I R plus C2. Okay, so there's the two equations we have and two unknowns, assuming we know this UI, which we'll get back to later. So solving these, we get C1 equals U dot big U I squared plus, oops, alpha I squared over logarithm of I. I'm skipping some details. Trust me, it's supposed to be this. C2 is easier. It's just minus U I R squared minus C1 logarithm of R. Okay, so I noticed with that we're using R as the radius of the drill hole, and Ri, that's the viscous forces. See the difference? So yeah, that's a bad pick of variables. So R without any subscript, that's a length, and R with a subscript, that's a viscous force. Okay, using this, we get I R I squared 1 minus R squared plus B1 logarithm R over R. That's what we're ending up with. Equations, that is the velocity field UI, is a function of the proportional, well, the proportion between the distance away from the, the distance away from the string, no, from the center of the borehole, and also the radius of the borehole, or the total radius of the borehole. And we still don't really know this big UI, because we don't know dz of the pressure. So that's next. Next we want to find this. Okay, so we'll assume that, again, back to this. We have that flow. So now I'm going to use more variable vi. We can measure this, so it should be known. I could substitute it, but it's basically this down here. So this is me being lazy and not writing it again on the blackboard. So this is, yeah, you already know C1, so it's this. So, yep, Q, you should know. UI, or big U, a capital UI, we're figuring this out now. We know the radius of the borehole, and we know the fraction of the drill string of the borehole, alpha I. So we have all of those components. That is big UI. Yes, so in the well can be known, or known. Because you're able to measure the flow inside this drill string. And it should be vi equals, this is something I'm found in the attic, I squared qi dots minus v without anything, and this is v without a subscript. This flow of the mud pumped into the drill pipe. Mud pumped into the drill string. So we also know this capital V. Basically what we're pumping in. Okay, so we also have another expression for vi by integrating ui over the annulus. So that's brown, I guess. So this brown part, that's an annulus. In the well. In the well is known. Get words sometimes. Okay, so we can also find this flow by integrating this ui over the annulus, over the donut. Integrating from alpha I r to r pi r small u r dr. Oh, let's see. That is a small u. And this should be okay to do. U pi I r r r squared r over r squared plus 1 ln logarithm r over capital R. dr. No? R, yes, dr. Okay, in order to do this more easily, I will do a change of variables. So I'll introduce a small v equals r. So then we have that v equals r over r or r r. Yeah, and just ask if my r's looks like v. The v, that's an r. Better r. Okay, so this one we can actually solve analytically. We should end up with y squared minus w squared, and now you might see why I keep writing C1, big thing down there. One fourth, 1/4 plus half alpha I squared. Let's up the parentheses. 1 minus 1/4 and find alpha I squared. Yep, alpha I squared and alpha I. Okay, so here we have the C1 there, which I won't insert, but you can insert it. The thing is, now we have two equations for VI, and they should preferably give us the same answer. They should preferably be the same. So, the last part. So you have I see what you mean. There. The end. Okay, so this VI and this capital VI should be the same. We can set them equal to each other. And the stuff that kind of falls out will be an expression of capital UI. I'm going to be a bit cheeky and say that capital I UI by I plus V or capital V pi R 4 times psi I. Then we're left to define phi and psi. Basically only to save us from writing. now I have a cheeky expression for ui, only I haven't defined phi and psi. So again, capital ui, phi, I over t 4 psi I, where phi I equals, let's see, -1 over 1 plus phi squared. And if you fall off, remember that I'm taping the lecture. This is a lot of minute details to write. Psi I 2 over, or maybe you're sitting with the notes, I don't know, plus minus squared no. Okay, and now I actually have an expression for mol ui, where I know everything. Who's getting a writing cramp? It's a lot of equations. Okay, so next I'm going to write the full expression for mol ui. Please bear with me. Function of r ui dot minus I 1 over I squared for the logarithm I logarithm of r, capital R. First bit minus phi I will be pi r power of 4 to 1 r squared minus 1 minus alpha I squared over logarithm of I r. Almost there. We also need the radial derivative of this velocity. And that is I r. Well, the only r's we are the only r's we have are the logarithm. So r r r r r are at the total part. 2I 1 plus yi minus alpha I squared logarithm I plus I over capital R squared R plus psi I capital V over pi R power 4 1 minus alpha I squared R I 2 over R. Okay, and then we're talking about friction force. Now we look at the friction force along or acting on a segment of string with length going to be again Ri, not capital Ri. I R without any index. H mu I over the R addition alpha I capital R plus Ri the function of thing you're filling in. Okay, so in order of it, R radius Ri friction force. Radius. Which is the, look my notes here, this RIdP of what's being pumped into it. This is the friction force acting on segment I from the inside of the drill pipe. And this term is generally equal for all of the segments except the last one, where you actually have some mud flowing out. Or the but it's going on through the valves of the drill bit. The end. And we're almost there. Keep this there. And basically we are going to end up something R I equals minus zeta I QI plus BI. Oh, let's see. BI pumped into it. That's what we want to end up with. Just a simple expression for this viscous friction force. The next, we have to figure out this zeta and this small vi. But we already have the equation for the viscous friction forces. We know 2, that's 2. We know pi, that's pi. We know alpha I, that's the fraction of the drill string occupying the drill hole. We know r, that's the radius of the drill hole. Mu, that's the viscous constant. I think. I forgot. Mu I is, yeah, viscosity. Just mu, that's viscosity. And we just had this monster equation for dui, dr, and we want to evaluate this at alpha IR, so at the end of the drill string, at the outside of the drill string. So we have all the tools, we just need to use them. And using them, get RI. Skip a bit here. H one plus I squared minus I squared logarithm over alpha I 1. Take the inverse of this, divide with how fast the drill string is moving, and add for mu plus we pump mud over r squared to phi squared logarithm alpha I over 1 plus phi I squared. A lot has to say with fraction plus phi I squared and logarithm of alpha I plus this. Bad thing about engineering, you get all of these complicated formulas. Plus this pumping stuff. dP of capital E. And are we able to match this stuff, this equation? I'm gonna wait. Okay, so we have this kind of like a monster expression over here. Though we know all of the variables, and also this kind of a monster expression, we know all of the variables. I'm going to say that this thing called data, data I, this thing called the I of capital V. And a quick like sanity check. See that, well, oops, it doesn't change sign. Equals. So see this Ri, it shouldn't change sign. Unless you actually suck mud out from it, then it doesn't change sign. So this thing we can actually control. This thing shouldn't change sign. And looking at this, well, h, that's a length, it's only positive. This is positive, it's a viscous force, and alpha i's between 0 and 1, between 0 and 1, between 0 and 1, means that this zeta I is always positive. So it still kind of makes sense. Next is actually trying to solve this system of springs. So now we are only focusing on one element of our drill string. Now we want to put it all together and look at so-called emergent properties. Because when you have a lot of stuff working together, well, stuff happens. So have you heard about emergent properties before? So it's like how cells can create a living being. Oh, well, cells are living beings, though, but how cells can create a human. So what's the difference between a cell and a human? Well, a cell is just one, a human is many cells. What's the difference between a person and society? Well, society is many people working together. Society has different properties than men, and men has different properties than cells. More properties, more complex. So the next thing is to actually rewrite all of our equations in a matrix form. Put everything in system. This also gives us a good repetition. So the systems of equations we actually have now is minus 0, 0, differentiated 0, b 0, k 0, q 0 minus capital Q plus k1, q1 minus q0 minus theta I qi dot plus bi 0 for the first one. For the next n minus 2, we have I q I double dots I b I q I q I minus 1 plus ki plus 1 qi plus 1 minus qi minus zeta I qi 1 plus bi. And the last element, n q n n minus q n minus 1 minus theta, theta n q n plus v. Those are all of our equations. Okay? So the matrix form of this is going to be capital M Q double dot as a vector plus E Q vector kappa Q Q minus B vector E vector equals some kind of driving force F of time. And next, well, tomorrow, we will just repeat a bit in the beginning, and then we'll try to figure out these matrices. So what we're going to do, we're going to create a set of equations to solve with these matrices, and then we're going to apply some transformations such that the system of equations we want to solve gets easier and easier every time. So I suggest you look at the notes on either on Blackboard or published on Slack. It's the one written by Sigve Hovda and Espen Raknes, called basically drill strings. Also, we'll be using some advanced math. Looking at eigenvalue decomposition. Advanced system. Questions? And if this seems interesting to you, if you want to look more on drill strings, again, Sigve, he's the guy. He sits in 3rd floor, 2nd floor. This is his child. And next week, we will start looking at the spectral element method and last, lattice-Boltzmann simulations. So we will have both drill strings and, well, geophysics and reservoir simulations. I'm not sure what there are most of our geophysicists. How many? None? Drilling? Any of you? 1, 2, 3? And reservoir, that's the rest of you? Okay, assume that. Questions?